All right, let's get into it. Today, we are pulling back the curtain on one of the most important pieces of internet infrastructure. We're going to break down how to design a distributed key value store, which is, and I'm not exaggerating, the secret engine behind so many of the massive apps you use every single day. You ever stop and wonder how that website, the one with billions of users, can instantly remember your profile, your shopping cart, or that photo you just liked a second ago? How does it keep track of all that data? Well, the answer lies in a very special and very powerful kind of database. And at its core, it's something called a key values store. The best way to think about it is like a gigantic digital coat check. You hand over your coat, that's the value, and in return, you get a unique ticket. That's your key. Anytime you want your specific coat back, you just show them the ticket. It's that simple, that direct, and that's what makes it incredibly fast. Okay, but what happens when that coat check suddenly has to manage billions of coats for millions of people all at the same time? A single warehouse or a single server just isn't going to cut it. It would be way too slow, and if it goes down, everything goes down. So the only real solution is to go distributed, to spread all that data across a whole bunch of servers. But the second you do that, the moment you spread your data out, you slam right into a fundamental law of computer science. You are forced to make a trade-off, a really tough, almost impossible choice between three critical guarantees. And this, right here, is where the real design challenge begins. So the first guarantee you have to think about is consistency. This just means that everybody sees the exact same, most up-to-date version of the data all the time. It's like having one single source of truth. If you update your profile picture, you expect everyone, everywhere, to see that new picture instantly. That's consistency. The second one is availability. This is the promise that the system will always respond to you. When you ask for your data, you get an answer. It doesn't just throw up an error because some random server in a data center somewhere is having a problem. The lights, for you, are always on. And the third guarantee is partition tolerance. This means your system has to keep chugging along, even when communication between its own servers gets messed up. And trust me, in the real world, networks fail. It happens all the time. Cables get unplugged, routers crash. Partition tolerance means your system has to be built to survive that chaos. And this all leads us to the big one, the CAP theorem. It's basically the fast, good, cheap, pick two rule, but for building massive systems. You can have consistency, availability, and partition tolerance, but you can only ever guarantee two of the three at the same time. You just can't have it all. Now, here's the kicker. Since network partitions are just a fact of life, they're going to happen. You have to design for partition tolerance. It's not really a choice. So that forces a direct trade-off between the other two. Are you going to build an AP system that is always on, but just might, serve you slightly old data? Or do you build a CP system that guarantees the data is always perfect, but might have to tell you to try again later to keep that promise? So, knowing you have to make this fundamental trade-off, how do you actually build one of these things? Well, it all starts with a really clever blueprint for organizing the data, how to spread it out across all your servers, and how to copy it so it's safe. To spread the data out evenly, engineers use a brilliant trick called consistent hashing. Just imagine all of your servers are placed on a giant invisible circle, or a ring. When a new piece of data comes in, its key gets converted into a position on that same ring. Then you just go clockwise around the circle until you hit the first server you see, and boom, that's where the data lives. It's a super elegant way to add or remove servers without messing up the whole system. Of course, storing your important data in just one place is a terrible idea, so we replicate it. After the data is written to its main server, the system automatically copies it to the next few servers it finds on the ring. That number of copies, we call it N, can be whatever you want it to be. This means if one server dies, your data is safe. Plus, it helps speed things up because now multiple servers can handle requests to read that data. Okay, so we've spread our data out and we've made backup copies. That's the foundation. But now we get to the really clever solutions, the techniques engineers use to manage that CAP theorem trade-off and deal with all the failures that are bound to happen in the real world. And this brings up a huge question, right? If you have multiple copies of your data living on different servers, how can you be absolutely sure you're getting the most recent version when you ask for it? I mean, what if one of those copies is a little out of date? Well, the answer is a strategy called quorum consensus. You can think of it like a voting system for your data. Here, N is just the total number of copies you have. W is how many servers have to say, yep, I successfully wrote the data, and R is how many servers you need to get a response from before you can call a read successful. And this is where the magic formula comes in. If you set your numbers so that W plus R is greater than N, you guarantee strong consistency. Think about it. The math ensures that the group of servers you read from has to overlap with the group of servers you just wrote to. There will always be at least one server in both groups, which means you're guaranteed to see the latest data. And by playing with these W and R values, you can tune your system for crazy fast reads or writes if you're okay with things not being perfectly consistent all the time. So what about server failures? Well, for short-term problems, systems use something called hinted handoff. It's like a friendly neighbor collecting your mail for you while you're on vacation. A healthy server holds on to the updates for its failed neighbor and just hands them over when it comes back online. For bigger problems, like finding out if data has drifted apart over time, they use Merkle trees. It's a way to summarize all your data into a tiny fingerprint. Servers can just compare fingerprints to see if they're out of sync, instead of having to compare every single piece of data. It's incredibly efficient.
Okay, we've gone through a lot of the theory. Let's put all the pieces together now and follow a single piece of data on its journey from the moment you hit save to the moment you ask to see it again.
So when you write new data, the first thing that happens is it's instantly logged to a file on disk. That's for safety, so it's not lost if the power goes out. Then, for pure speed, it's also put into a super fast cache in memory. And finally, every so often, that memory cache gets neatly sorted and saved to a permanent file on the disk, locking it in for good.
And when you want to read data, the system is smart. It checks that fast memory cache first. If your data's not there, it asks a very clever bouncer called a Bloom filter. This thing can't tell you for sure if your data is in a file, but it can tell you with 100% certainty if it's not in a file, which saves a ton of time. This lets the system narrow down the search and pull the data from the right place on the disk. So let's just quickly recap the big ideas. Key value stores are absolutely essential for the modern internet. The CAP theorem forces every designer to make that crucial trade-off between being consistent and being available. And finally, it's a whole toolkit of clever ideas like consistent hashing, replication, and quorum that all work together to build systems that can actually handle the scale of the internet. And this is where it gets really interesting. The next time you're scrolling your social media feed and it takes a split second for a new post to show up, or when you make a bank transfer and it's reflected instantly, everywhere, stop and think about it. Are they choosing availability over consistency or the other way around? What trade-offs are the apps you use every day secretly making? Something to think about. Thanks for joining me.